Okay, welcome to the world of hardware modeling. So, as you know that modeling the hardware consists of an important aspect of knowing the details of the behavior of the hardware, the structural interconnections of the hardware. So, just by using a paper and pen approach for analyzing digital circuits is not sufficient. So, one of the important aspects of learning hardware is to learn how to model the hardware, how to model the interconnections between the different components in the hardware. So, in this course, we'll focus mainly on using Verilog, which is a popular hardware description language. In fact, in the industries, a lot of people like to use it as a hardware description language, and we'll be using Verilog as a modeling language for modeling the hardware. So, we start with the notion of how to look at hardware from the perspective or from the point of view of modeling, and then we'll enter into the details of Verilog and how do we model the different systems in Verilog in the structural, behavioral, and data flow styles of modeling. So, we start by asking ourselves the question that what is an electronic design? Given the specifications of a system, we would like to develop a circuit by knowing connecting known devices such that the given specifications are being met. Now, then the next question is, what do we really mean by specifications? Specifications mean a lot of things. So, when people talk of specifications, the specifications mean something with respect to a prosaic end user. On the other hand, to an engineer, it means a lot of things. It means an unambiguous set of clear specifications such that given those specifications, an engineer can ultimately be able to build the system. So, with respect to our particular digital system design, specifications refer to the description of the circuit, either in terms of structural interconnections or in terms of behavior of the circuit. So, electronic design is the process of converting a behavioral description which pertains to answering the question what happens when to a structural description of the circuit, which means we need to answer the question what component is to be connected to what component, and so on. So, apart from structural design, we also need to do physical design, which involves choosing device sizes, placement, routing, interconnects, etc. So, the main challenge of a modern electronic design is the circuits that we want to design, which are extremely complex. So, if you talk of circuits in the days of 50s and 60s, people used to talk of circuits which are having one transistor, 2 transistors, or 10 transistors. Today, we talk of processors which have got few million transistors sitting on the IC. So, naturally, the complexity of circuits is exponentially increasing across the years because our demands are unending. In few years, the complexity of circuits will become comparable to that of living systems. That is a very optimistic way of thinking about how the complexity of circuits is growing over time. While the technology has moved over a rapid pace, capabilities of human brain have remained the same. So, systematic methods must be developed to conquer complexity. So, what to do to suppose I give you an assignment of designing a processor at the transistor level that has got some 50 million transistors sitting on it, then perhaps all of you will leave the classroom at the first glance. So, naturally, the conventional pen paper approach does not work well with especially when it comes to designing and modeling integrated circuits. So, naturally, our goal would be to find out some other systematic approaches by which we can cut short the time needed to design the circuit. So, one way out is to take an experience, share the experiences of a software engineer, and and the way he trains himself up to develop a software. So we need to make use of notions like hierarchical design, modular architecture, text-based rather than pictorial description, and also for ultimately the reusability of existing resources, which will minimize the development time to a considerable extent. The main problem that comes with respect to hardware, which basically discriminates it from any kind of software, is the concurrency in the hardware. So given that n number of signals are there which provide input to a hardware, all these n number of signals should receive input at the same instant of time, and when there are n number of parallel paths sitting within the system, all these n number of parallel paths are supposed to compute together. However, in case of software, it basically involves a fetch, decode, execute paradigm, where you index into a certain location of the program memory, fetch one instruction, decode it and execute it, and then fetch the next instruction in sequence. Hardware behavior has timing and integral part. Traditional software is not timing sensitive. So hardware description languages need the ability to describe, simulate at behavioral, structural and mixed level, and to synthesize. The designer rapidly decomposes the system level specifications into groups and subgroups of simpler tasks. The lowest level system tasks are implemented in silicon with standard circuits that have been previously designed and tested. In the top-down design methodology, we first define the top level block and then keep on rapidly decomposing the modules into sub-blocks and sub-sub-blocks, ultimately arriving at the elementary level blocks, which are called the leaf cells. The leaf cells are those cells which are fundamental enough such that they cannot be divided. So in the top-down design philosophy, we aim at dividing the modules repeatedly until we arrive at the leaf cell level, such that we reach to modules which cannot be further subdivided. The designer in case of bottom up approach, it's just the opposite, which means the designer starts with a single transistor implementation of a small part of a circuit and keeps on adding components over and around it, ultimately reaching towards the entire circuit. So while a top down approach is more divide and conquer oriented, a bottom up approach basically aims at starting with the elementary level components and integrating components over and above it, ultimately reaching to the final thing. But in case of bottom up approach, the modules are interconnected to realize the required functionality. So in case of bottom up, since we start with the single transistor implementation of the circuit and go on adding components over and above it, so it basically leads to better a more optimal implementation of the circuit. But whereas in case of the top down design approach, although the approach is quite fast, where you keep on rapidly decomposing the system into modules and submodules, the time for realizing the circuit may be less, but you end up reaching some suboptimal solution to the problem requirements. Top down approach is better suited for digital design. However, bottom up approach is better suited for analog design, and so the combination of both is the typically chosen mode. So in case of bottom up approach, as you can see from this block diagram, we start with the leaf cells, which are the elementary blocks of the circuit, and keep on integrating the multiple leaf cells together into sub blocks and multiple sub blocks together into bigger level blocks, ultimately arriving at the design of the whole system. So example is the case of a 4-bit ripple carry adder, where each of the bits in the 4-bit adder comprises of one full adder, and each full adder is composed of XOR, AND and OR gates. So you start with the design of XOR, AND and OR gates, then you put them together to realize the full adder, and then put the full adders together to realize a 4-bit ripple carry adder. So this is how you go by the bottom up design philosophy. In case of the top down design philosophy, you start with the design of a 4-bit ripple carry adder, and then split it up into 4 full adders, and then with each full adder being divided into XOR and OR gates. There are two approaches of the design. One is the top down approach, which has the advantage of speed. The bottom up approach has the design of accuracy. So, in order to have a good compromise between the two, a combination of the two is the typically chosen method. Now, given that you have a particular design problem, there are different phases of the design problem one needs to pass through. At the top level, we need to have the algorithmic and system level design, where you start with a formal description of the system in hardware description language, and then you give a procedural description to it depicting the behavior of the system. And finally, you have to simulate the design with the help of a simulator to detect the errors present in the specifications, and then use a synthesizer to generate equivalent logic netlist. So, the typical chosen approach these days is the hardware software co-design, because you choose the critical parts of your design and implement it on hardware, where you have the regular concurrent flow of instructions through multiple parallel data paths. On the other hand, there are non-critical parts of a system that need not be implemented in hardware, otherwise that would escalate the cost of the system, but that can be implemented based on a fetch, decode, execute paradigm. So, you can have systems like an FPGA and a processor talking to each other, where the FPGA is implementing the hardware part of the system and the processor is implementing the software part of the system. The netlist is synthesized from the synthesis tool or the schematic editor, and then the simulator is supposed to check the errors in the design. This is done in the structure and the logic design phase. In case of transistor level design, we need to focus on the physics of operation of the circuit, where the circuit is visualized as a collection of transistors, and then we need to characterize various things such as the switching characteristics, the timing simulation, as well as the entire circuit simulation, where we use accurate transistor models in terms of nonlinear differential equations. Finally, once we have the transistor level design of the circuit, we need to go through the different phases of physical VLSI design. Physical VLSI design again comprises of 5 phases: partitioning, floor planning, placement, routing, where the routing is again divisible into 2 phases: global routing and detailed routing. Partitioning keeps tightly connected subblocks in the same place and helps in floor planning and placement, where you choose a large problem and decompose it into sub problems of manageable size, so that they are implementable using the limited memory and limited speed of the processor. At the floor planning and placement level, a definite block is assigned to each module. So, the area and the location of the different components in the design are fixed at the floor planning and the placement phase. In case of the routing phase, some wiring patterns are generated for correct interconnections and aims for minimal area. Design rule checkers are used to check mask geometries. Circuit extractors are used for checking the final circuit from the mask layout and then simulated for verifying the functionality. So, naturally, we understand that simulation is very much indispensable for verifying the correctness of integrated circuit design at different steps, and these simulators also help us to verify the functionality and timing of the chip before fabrication and allow easy modification of the circuit components. So, if you look into the modern VLSI circuits, it consists of thousands of transistors. The Pentium 3 processor had 65 million transistors, and the Itanium had 320 million transistors. So, naturally, the traditional breadboard method fails for VLSI circuits, and there is a popular joke that if you suppose you and your friends and work with a company where an IC is fabricated only to be discovered during the test phase that the design is faulty, then there is no other way than to just lie down before the God and pray before the God. In fact, 70% of the total design effort spent for bringing out a chip is spent only during the design phase and rest 30% during the fabrication phase. So it has to be spiced before it is cooked and spiced well and many times before each stage of the design and after each design step by simulation. So this is called analysis. Analysis states the quality of synthesis, and SPICE is a simulation program, and it is also an analysis tool. So there are two popular hardware description languages to model digital systems. They are Verilog and VHDL. Using Verilog, one can design, simulate and synthesize. Concurrency, timing and clocking can all be modeled, can handle asynchronous as well as synchronous sequential circuits, and finally the logic, operation and timing behavior can be simulated. Now if you see the design flow for the hardware, you start with a hierarchical description of the system, and then you do the active coding where you look at the system, identify the different modules and code them individually, then you compile them, you simulate and verify them. So this iteration should continue for a couple of times until you are convinced that the front end output is what you are looking for or what is the exact desired one. And finally the compiled output is simulated or verified and then sent to the tool for placement and routing, and once the placement and routing are done, the timing verification has to be done once again to check whether there are any signal integrity problems or not, and this becomes very critical, and many a times lot of money is wasted because of incorrectness in choosing the right component for the right problem. So you see a simple Verilog code in this slide where we have tried to implement a 2-to-1 multiplexer. As you can see, there are two inputs, one output and one select input. So that is what we describe using the declaration syntax of the module, which is basically module name, and then within bracket you write the parameters you want to obtain as output. So next you need to describe what are the input and what are the output ports, and since this is a case where you need to consider both input 1 and input 2 or select input, therefore you find out whether the output is equal to input 1 or input 2 depending upon the select input, so that the circuit behaves as a 2-to-1 multiplexer. So that what it is the basic building block in a Verilog code, that is the module. The module is created by declaration so that it cannot be nested. It can be used by instantiation. Interface is defined by ports. So there may be ports, there may be blocks in a module that contain instances of other modules. All modules at the end run concurrently. So to look at an example, you can see that in this example the function, the module adder is called in the main module, and then an instance add underscore 0 is created with out 0 output and in 1 and in 2 inputs. A module provides a template from which one can create multiple objects. When a module is invoked, Verilog creates a unique object from the template. Each object has its own name, variables, parameters and I/O interface. So next code is a full adder program where carry out and sum are the two outputs, and A, B and C underscore I are the inputs. So we do the connections following a ripple carry adder and then check for correctness of the connections. So now Verilog is a case sensitive language, which means that if you change the case of writing the program, it will give errors. If you use a mixture of upper and lower case letters, it will give errors. The identifiers are can be digits like from 0 to 9. It can be underscore, it can be our upper and lower case letters from the alphabet. So these are the single line and double line, multiple line comment arrangements like C. Verilog is case sensitive. So if you talk of the registers in a typical Verilog program, then the registers are the typical units of storage in case of a Verilog program, and then the keyword reg is used to describe a register. Apart from that, integer, time, real are also used. In case of Verilog, we rely on event driven modeling. That means any change in the code occurs, it will immediately evoke that part of the code, and that is actually being executed. However, for modeling sequential circuit, a different approach of storage element is used. Assignment is always done in always block. In case of Verilog, the data type net basically stands for these variables, but they are basically equivalent to signals in VHDL. So typical keywords for Verilog are wire, wand, watt, try, triant, triode, supply 0, supply 1. The input, output and in-out ports are by default called wire. So now coming to the different styles of modeling in VHDL, there are three different styles of modeling: structural modeling, behavioral modeling and data flow modeling. So let's look at a hardware and see how it is actually being modeled. So given that you have an hardware, at the top level you only like to give a black box description of the half adder, which means that you define the input and output ports. So there are 2 input ports and 2 output ports of the half adder, so which is actually laid down over here. And then in case of data flow style of modeling, you basically look at the circuit from a signal detection point of view. So so you check the 2 inputs, and if the 2 inputs are similar, then the sum output should be 0. If the 2 inputs are different, then the carry output should be AND of the 2 inputs. Now coming to the behavioral style of modeling, we basically model the entire system in the form of flowchart, where we start with some start at a point and then input the 2 data A and B, and then see if one input is equal to 0. If one input equal to 0, we check whether the other input is equal to 0 or not. If the other input is also equal to 0, then we have the 4 combinations. The sum is 0, carry is 1, sum is 0, carry is 0, sum is 1, carry is 0, sum is 1, sum is 0, carry is 1, and then finally you output S and C together. So this is the behavioral model of the half adder circuit. As you can see that we are first checking if A equal to 0 or not. If A equal to 0, then the carry then one of the input is equal to 0, therefore the carry must be equal to 0. Otherwise the sum equal to 1. On the other hand, if A equal to 1, then I am checking if B equal to 0. If B equal to 0, then sum is 1, carry is 0, else sum is 1, carry is 1. In case of structural style of modeling, I basically look at the half adder as an interconnection of a 1 2 input XOR gate and 1 2 input AND gate. So as you can see that structural model is very easy to implement. You need to find out what are the kinds of gates being used and how are they connected. So in coming to the 4th type of modeling, which is also called the mixed style of modeling. So given that given that you have the different styles of model, at different contexts you would prefer to use one model or the other. So, in case of mixed style of model, you have to take help of multiple modeling styles. It can be a structural or behavioral mixed, behavioral or data flow mixed, structural or data flow mixed. So,